Okay, this first one? Major difference between alpha and beta? That's not the major difference. Okay, that's one. This will that'll transmute the element. I don't disagree with that statement, but that doesn't answer the question. Okay, so I'm not asking about the difference between alpha and beta. I'm asking about the difference. Alpha and beta are in one class. Gamma is in another class. The alpha and the beta are things. They're like actual physical objects that come out of the nucleus, where the gamma is just energy. There isn't anything to like capture or store or interact with. It's just light energy. Isotope? Wrote that. I don't actually have to have two things to talk about isotopes. I'm saying every single atom in the universe is an isotope. But which one is it? Is it carbon-12? That's an isotope. Is it carbon-13? Is it carbon-14? Is it uranium-235? Is it uranium-238? Each of those is saying uranium or carbon, which is telling you the number of protons, and then giving you the mass tells you, after some subtraction, the number of neutrons in there. And it matters. Why? What? Yeah, why does it matter that these things have different numbers of neutrons?
Affects the density of the nucleus?
Not the density. Level of radiation? It's not a sliding scale. It's a go, no go. Really. Is it radioactive or not? So what's the radiation, what is it dependent upon? You okay with that? It's not about having too many neutrons. It's not about having too few neutrons. It's about having the Goldilocks of neutrons, right? Not too many, not too, just the right amount. If it's got just the right amount, then it's totally stable, it's not radioactive, and everything's fine. But if I don't have enough or I have too many, then I'm going to be radioactive. No, like carbon-12 is not radioactive, neither there is carbon-13. So a lot of the elements have more than one isotope that are not radioactive, but not a lot of them. Like most of the isotopes are radioactive. But then again, most of the isotopes are unusual, not something that you would find. Like you're not going to find, say, a carbon-4, a carbon-8, something that's got 2 neutrons and 6 protons in it. That's just not going to happen. So maybe somebody made that atom, that isotope, and maybe it existed for like a millisecond, but it's not something that's important. The ones that are important are the ones that stay radioactive for an extended period of time, that don't just disappear in moments. Okay, so what's this 20F9 tell you? So mass, protons, this is protons plus what? Neutrons. So I know my neutron number, right? So if I know that this is 9, then I know that's got to be 11 because I just told you that this thing equals 20. So then type 2, it's just 20 with an F, and then type 3 is F with a dash 20. Okay, electromagnetic wavelength, 5.5 times 10 to the negative 5th meters. What are you doing with that one? Is it radio waves? No?
Microwaves.
Microwaves? So this would be microwaves. Really? Is it microwaves? I'm pretty sure, yeah, pretty sure it's infrared. Because it's about 700 nanometers is red. You okay with that? So that would be 700 times 10 to the negative 9th. So that would be 7 times 10 to the minus 7th meters. And that's the end of the visible spectrum. And so then at 5, what would that be? If it was 10 to the negative, so it would be 2, so it would be 0.05 times 10 to the minus 7th. You okay with that? I just turned the 10 to the minus 5th to 10 to the minus 7th. So what I'm saying is these two things are pretty close to each other. They're off by about 2 orders of magnitude, and that sounds like infrared to me. You okay with that? Did I mess that up? I totally messed that up. Thanks. It's 5500 times 10 to the minus 7. That's better. It had to be a longer wavelength. Yeah. How about this blue light, green light? How do you know that blue has more? Just from looking at that table. How about this? Infrared, okay? Then what comes after infrared? You okay with that? And then what comes next? UV, all right with that? So which one of these has more energy? This or that? This one over here is the dangerous one, right? Biologically. So what's blue closer to? Blue's closer to that, so it's got more energy. That's the easiest way for me to think about it. And as far as wavelength stuff goes, it's got blue has a shorter wavelength. And since it has a shorter wavelength, tell me about its frequency. A higher frequency since they're inversely proportional to each other. You good with that? Write all 3 types of information about the 22 neutron potassium. So I got a K, I got a K, I got a K. And so what do I put right here? $19? What do I put right here? Nothing. Up top? 41? Okay with that? So then there's a 41 here, and there's a dash 41 here. There we go. There we go. Whatever. Missing. Cool. So treat this arrow as an equal sign. So whatever's on one side has to equal whatever on the other side. So this over here has to be a 14 because 0 plus 14 is 14. And this has to be a 7 because -1 plus 7 equals 6. And so then after you've done the math, then look at it and say, what element do I have? Well, I just look at the 7, that tells me it's a nitrogen. What fundamentally happened? Okay, the next one, the numerator, or the superscript. What should he write there for the superscript? 228. And then the subscript? 88. And then what's that? Radium? Okay with that? So that process of alpha decay, which is what the second one is, a particle leaves the nucleus. That particle consists of 2 protons, and then the rest of the mass is neutrons, so 2 total neutrons. What has a mass of 2 protons and 2 neutrons? A helium nucleus. So if you took, so there's a rock called pitchblende that's got uranium in it. I mean, these are just elements, so you could literally dig up a rock that's got uranium as part of its components. Why might that rock draw your interest? It's glowing in the sun, in the dark. It's like emitting light. Great. So it's emitting light, so you might take this thing with you and go somewhere. If you were to put it into a container, that container would start to fill up with helium. So if you took one of these and you're like, oh, this rock, and I got this cooler, and I put it in a cooler, and I close the lid, what's going to happen? The top of the lid of the cooler is going to pop off as the cooler's interior fills up with helium. It's helium because that's what an alpha particle is. The only difference between the helium and the helium nucleus is this has got a +2 charge. Why? It doesn't have any electrons with it. It left as 2 protons and 2 neutrons. But I've got radon over there with a atomic number of 88. So how many electrons does it have? 88, right? And now it turned into radon with an atomic number of 86. So how many electrons does it have? 86. What happened to those other 2 electrons? The radon was like, don't need you. I'm a noble gas. I definitely don't need you. So I've just got stray electrons just randomly in this container. What might happen? Those positive charges of the helium will grab those things, of the helium nucleus. So initially it's just the helium nucleus, but since the thing that it just left now no longer wants 2 of its electrons, those electrons are just dumped to the environment and it takes them. And so you actually do have helium. Yeah.
One thing I wasn't clear last time, is it like 99% of the time it's a helium as an alpha particle, or every single time?
Every single time. An alpha particle and a helium are the exact same thing. Helium nucleus. You need to think about it because it's going to take it a moment to grab it. So initially when it comes out, this is a positive charge. And when the electron from the beta particle leaves, it is a negative charge. So that nucleus of the carbon-14 let an electron leave. Okay? How many electrons did the carbon need? 6, right? It's carbon, it's got 6 protons, needs 6 electrons. Tell me about the thing that was made. It needs 7, right? It's a 7 proton atom, nitrogen. So does it have 7 electrons in orbit around it? It only has 6. So that's actually a neutron with a positive charge on it. Not a happy camper. So what does it do? It scavenges that beta particle, picks it back up or takes it from some other atom. And eventually that beta particle turns into just a regular old electron orbiting a nucleus. Yeah.
So I'm a little confused on the potassium between 2 nitrogens. I mean, neutrons.
What about it?
potassium.
With the 22 neutrons? What's wrong with that?
Why is it 41?
Did I not do my math right? 22 and nitrine is 41, isn't it?
But doesn't it have a mass?
Why would it have a mass of 39?
That's 22, the 22 neutrons.
Are you talking about on the periodic table where it says 39? This 39 right here?
Yeah.
What does that 39 mean?
Um,
Its weighted atomic mass is 39. So it means since every single potassium has 19 protons in it, what do most potassiums have? 20. We okay with that? But this one has 22 neutrons in it, so its mass has got to be more than 39, but 41. So that is an isotope of potassium. But most of the isotopes of potassium only have 20 in it. But that doesn't mean that 22 doesn't exist. Yeah.
So is that nitrogen's got a +1 charge?
Yeah, so technically this guy here has a +1 charge, and then at some point it's going to gain an electron to become just regular old nitrogen again. So this last one?
It's to damage the DNA. So,
In what fashion? The DNA must be damaged how? You got to break a chemical bond. If the radiation that is being exposed, that the DNA is being exposed to, is not powerful enough to break a bond, tell me about the cancer ability of that radiation. There isn't any. It can't. So if a bond can't be broken by that radiation, that thing can't cause cancer. And what's the cutoff in the electromagnetic spectrum? The cutoff is visible light, sure. Anything that's visible light or longer cannot break a bond in DNA. So anything that's shorter than that can. So UV, X-ray, gamma, cosmic, any of those things could. The neutron? You okay with that? So we're talking about like a thing with a thing on it. Negative thing, positive thing. When negative thing leaves, I have a proton left.